310 on my computer. So while we're waiting, I just finished talking to a federal investigator about a student who took this class 2 years ago who was applying for a security clearance, which I've never done before. So I came back after class on Tuesday, and there's like this little sticker on my door, like from something that looked very official with like eagles and flags and stuff on it. I'd like to talk to you. And so, yeah, it was a very interesting conversation. So if any of you are thinking about applying for federal jobs, don't let me know about anything bad that you do, and that'll make things a lot cleaner. But it was fun. She was very nice. It was a good conversation, and I hope the guy gets the job.
Oh, we saw that. Yeah.
Okay, so this afternoon we're going to do a little OpenGL tutorial. So basically the way this is going to work is what I'm going to tell you about for the next hour and a half is why OpenGL was done in the way that it was. And then at the tutorial, I'm going to tell you how it was actually implemented. Okay, so this is more of the why, and then we'll do how. So you know OpenGL already? No need to show up. Those people who do show up, looking forward to having you. We'll order some pizza for the end. We'll do that right at the beginning, and it'll get delivered near the end, and we'll have a good time. And basically what I'm going to do is talk a little bit about OpenGL structure at that point, sort of how you structure programs and what the pieces of OpenGL are, and then we're going to walk through some sample code. Okay. Assignment 1, which is this writing assignment, is due Tuesday at 10:30, so before class. Submit this via SmartSide. If you have some sort of research thing that's keeping you from doing that, and you're totally swamped, please talk to me. But it's best for all of you if you get this out of the way quickly. Assignment 2, I'll post sometime this weekend probably, and that's going to be an assignment that will be a characterization assignment. So you're going to characterize your graphics card, do some measurements of it. Okay. What I would like you to do sort of before the next week, so maybe before next Thursday or something, find a computer and a compiler and a graphics card that you can use together. And it should be a reasonably decent graphics card. Just a regular laptop's graphics card is fine. Just don't go get something that's 10 years old that does 2D graphics only. Okay, so anything you have today is probably going to be okay. And then you can go get off the software resources page a piece of source code called Graphics Bench. And this was written at Stanford for doing benchmarking stuff. And I want you to download it and compile it and make sure you can build it on your machine. So that just tells me and you that you have a machine you can use and a compiler you can use, and you have all the pieces you need to be able to actually use this thing. So do that before next week. And the reason I want to say that is if we have problems, we can work them out sooner rather than later. Any questions administratively? Great. Okay, so it's all lecture from here on out. Okay, so what is computer graphics? So computer graphics is taking a scene description, like this one here. Okay, and this is a RenderMan code. And it's RenderMan code that describes the surface of that beach ball and turning it into an image. So we take some sort of 3D description of the world, and we turn that into a 2D image. There's a lot of different ways we could think about writing software to do that, and I'm going to talk about that today. So what are possible ways that we could build a graphics system? So this is the opposite problem of something like computer vision. Computer vision is you take a 2D picture of the world and you try to figure out 3D information from it. Okay? This is the opposite problem. We take 3D information and we develop 2D something for it. And this is one possible way that we could organize it. So this is organized in such a way where you describe surfaces with some sort of description. Okay? So here we separate out the geometry from the surface. Okay? Here we only are describing what the surface looks like. Okay? But there's different ways we can do it, and we're going to be talking about them today. Okay. So the first part is where I'm going to talk about how we do this structure. So API decisions. So what should the programming interface to a graphics system look like? And then the guys that wrote OpenGL, which is the interface we'll use for explanations for most of the course, is they wrote a nice paper talking about not just what their system was, but why they did it in the way they did. So what were their goals as designers of OpenGL? And then I'll spend 20 minutes or so going through the graphics pipeline and saying, okay, in OpenGL, here's the steps of the pipeline. Okay, here's what actually happens on each step. So Even if you can't make this afternoon's session where I go through OpenGL code in general, hopefully this is going to give you a good idea. So this is roughly what I want you guys to write about. And I don't want you necessarily to take my slides and just walk all the way through it. You're writing it for the layman after all, and you guys are not laymen. But hopefully it'll give you an introduction and a good place to ask questions if there's things about the pipeline you don't understand. And I don't think I'll get to this, but just how much do each of the pieces of the pipeline cost? What are you actually doing at each stage? So if we get to that, we'll talk about it. If we don't, no worries. Okay. So one of the first things we have to decide is how do you specify a scene? Okay, so we need to talk about the scene that we're rendering, and how do we do that? And so there's sort of two different ways we can do that. One is sort of saying, this is sort of a higher level way to do it, a declarative way to do the scene. So what is actually happening in the scene? And the example I have here is a virtual camera. Okay, so we're going to describe the scene from the point of view of a camera. And we're going to do that by describing sort of this virtual camera. So here's this camera, here's the position of the camera, here's the field of view of the camera, here's the aspect ratio of the camera. So you're sort of saying, what is going on? Okay? And the underlying programming system is going to figure out how we actually go out and do that. So, okay, well, given that the field of view is this, and given that the aspect ratio is this, then we can derive this about the way we have to do all our view transformations and so on. Okay? So this is a higher level view to do it. And so if we look at like a scene graph kind of interface, right? So what's a scene graph? A scene graph is I have to draw all you guys. In fact, I have to draw everybody on the whole campus. And there's 30,000 students on this campus. Right? So I'm going to have some sort of nice graphy kind of structure that defines all those students. And they're all going to be sort of sorted out based on where they are. And then I can look at I can say, well, I'm only in this room here. Let me take this chunk of the graph that only has the people in this room, and then I don't have to worry about the other people. Okay? So as a programmer, all I have to do is put a bunch of stuff in the scene graph, and then tell the scene graph, okay, I only want this subset of geometry in the scene graph, and the system figures out how to give me the right subset. So I'm sort of saying what's going on, but I'm not saying how it has to be implemented underneath.
Is that like quad trees and oct trees?
Sure, so that could be used to implement a scene graph, for instance. But as the programmer, I don't know if it's implemented with a quad tree or an oct tree or some sort of binary balance tree or red-black tree or any other thing. I know what the behavior is, but I don't know how it's implemented underneath. Okay? Or I can do the more OpenGL style thing, which is I'm actually saying how things work. Okay? This would be the analogy of actually having a quad tree or an oct tree or something, where I say, okay, these are actually the data structures that I'm using. Here's the algorithms that are going on. I'm going to have to give the hardware drawing commands. My job as the programmer is actually to come up with that list of drawing commands and send them to the hardware. Okay, so instead of having a virtual camera, what I'm going to have is say, well, what it actually comes down to is I'm going to do a lot of viewing transformations, and I'm going to express those as matrices, and we'll see that later in the lecture. Okay, I'm actually going to specify what those matrices are. Okay, so this is closer to the hardware. And so this is a decision that needs to be made. And the people that implemented OpenGL decided that they are going to be closer to the hardware. Now, one of the nice things is that you can build a declarative interface on top of an imperative interface if you want to. So, for example, these scene graphs here that are done in these two formerly SGI products are actually built on top of OpenGL. So, hey, this is too low level, and we know some of the mechanisms we want to do to abstract it. We're going to do it this way instead. Yeah? Microphone.
Are we assuming the data that we're going to use is going to come through a camera, or is it going to start from scratch?
Well, so your job as the programmer at hire is to say, here's the things that are in the scene. Okay? Here's where the camera's going to be. And then somebody is going to figure out which things are going to be rendered and which things aren't, and which order you're going to render them in, and so on. So that could be you. It could be the hardware. It could be the programming system. Could determine all those things. Okay. So we make this decision as far as the API goes. And then we say, okay, well, what are we actually going to render? What are the primitives in our rendering system? And so one thing we could say is, well, what we're actually rendering is the real world. And the way things look is entirely determined by how they interact with light. So why don't we make light our fundamental rendering primitive? Okay, so our fundamental parameter is going to be photons shooting all over the scenes, or rays that are shooting all over the scene, and we will calculate how each of these rays or each of these photons interacts with things in the scene and eventually comes back and reaches our eye. Okay, and you can build a rendering system this way. And if you do, it's ray traced. Okay? And people will build ray tracing systems, photon mapping systems. There's a number of different ways that use light transport as a basis. So I think it's a beautiful picture. This is all done computer rendering. And so, I mean, the light transport here is really cool. And so light's going in, bouncing around, and so on. It turns out, theoretically, this is a really nice way to do it. Because if you think about the way you're going to render this, you're going to send in rays, okay, into each pixel, each individual pixel, and they're going to bounce around, and then you can calculate the whole thing. And so the complexity of this rendering is proportional to the size of the screen. Right? If I double the size of the screen, I'm going to have twice as much work to do. Okay? And so that's a nice growth curve to have. Okay? That's a good thing. It is different than what we're going to talk about next, which is rendering every piece of geometry. Because if you make the scene twice as big, then it's actually going to sort of expand in three dimensions, and there's going to be more and more objects to render and so on. And theoretically, this grows slower than something that's actually based on geometry. But the sort of constant factors in front of the O of n or O of n squared kind of rendering here are very large. And so people have started to look at doing real-time ray tracing things, but anybody who's seen the pictures just don't look as good as what you can do in real time using graphics hardware. But the GPU companies are very interested in being able to do ray tracing kind of effects in real time, and that's a really big area of research right now. Okay, so this is not what we chose. Okay, this is not what we do for real-time rendering stuff. Okay, here's another thing we can look at. We can say, well, what we're doing is we're drawing pictures. So the fundamental primitive in our rendering system should be pictures. Okay, so what we're going to do is we want to render this room. I'm going to go around with a camera, take a whole bunch of pictures, stand in different places in the room, take a whole bunch of pictures, and then when it's time to render it, what I'm going to do is put all these pictures together, do warping, so I can make sure that they look good, composite them together, and it's going to look really cool. And so this is a project done at the University of North Carolina, and it sort of shows, I think it's like rendered from over here, and so there's pieces that you don't have there, and we're looking at it from a different direction. So there's some neat things about being able to do image-based rendering this way. One of the nice things is that you can take a picture of something really, really complicated, and it's a pretty simple picture, right? It's just an image. You don't have to model the complexity that's inside that image.
Is this what Microsoft Photosynth does?
So I would say Photosynth is awesome, by the way. It's one of the coolest things Microsoft's come up with. So basically what you do in Photosynth is they have a demo of a cathedral in Rouen. I don't pronounce French at all, but it's a cathedral in France somewhere. And so they took thousands of pictures they got off Flickr. And they were able to sort of derive where every picture was taken from. And you can sort of fly around the scene, and it warps from picture to picture and sort of blends them all together. So it looks like you can sort of go 3D through this entire scene. It's really cool looking, and I definitely recommend taking a look. It's a very computationally intensive process to build. Once you have all those pictures, it takes hours to like put them together where you can actually fly around. But it's really cool. It's a great research project. To some degree, that's an image-based rendering thing. I don't think it's really designed as a graphics system so much. But I suppose you could probably use it like that if you wanted to. You'd have to do a lot of pre-processing to make it work, but it is an image-based rendering program for sure. North Carolina did sort of the seminal work on this stuff. They never really built any hardware for it, but it's a possibility. And if you look at the way people do texture mapping in graphics, to some degree they're using images as a rendering primitive. Okay, but you can see it's got some problems. I mean, if this door is shut and I take a picture here, I'm never going to know what's on the other side. You know, I mean, if there's information you don't have in your pictures, you're not going to have the information you need to draw the scene. Okay, so what we actually choose to do is geometry. Okay, at least in real-time rendering systems, the sort of GPUs in your system today, the fundamental primitive is geometry. Okay, so. Question is why? Why does geometry end up being well suited for real-time rendering? Okay, what's interesting about geometry? Why does this end up being efficient?
Implement it in hardware.
You can implement it in hardware, which is kind of a tautology, but what is there about geometry that makes it well suited for implementing in hardware?
You can describe fewer things rather than describing all the pixels on a sphere. You can just describe like the radius of the sphere.
Okay, So potentially there might be less information you need to describe an object. Although if you have a complicated object and you model it with geometry, then that's potentially a lot of complication. But it's possible. There's certainly objects you can define with not very much information in terms of geometry. Okay. What about from a computational point of view?
Each piece can be handled independently.
Okay, so this is one of the enormous things that if I'm rendering each of you, okay, you're all separate. I have parallelism when I render you. I can render every single person separately, and you don't have to know about you to do the rendering. Okay, so it's not just that it's parallel, it's that it's parallel and independent, that I can render different pieces of things all at the same time, and those pieces of things don't have to know about each other at all.
You can say the same thing about ray tracing because each pixel doesn't have to know about the neighboring pixel to be rendered.
So this is true. So we do ray tracing, and so every pixel is independent. But what is not independent is that for every pixel I render, I potentially can touch every object in the scene. Okay? So every primitive that I render has the possibility of requiring global knowledge. That you know everything because light could potentially bounce anywhere. And so that's very difficult from a hardware point of view to render, to implement, because that global knowledge is very expensive. You have to go out to main memory, you have to page things off disk, and so on. Okay? What's nice about geometry is to render this globe here, I only need to know about the globe. I don't have to know about the rest of the world. That's what's really cool.
So conversely, if things are going really bad for you, then every piece of geometry could touch every pixel on the screen, too.
Yes. And so one of the questions is your rendering complexity determined by the size of your screen or the complexity of your geometry?
Right. So back on the ray tracing thing, I was going to argue that depending on the number of bounces that you have in the scene, if you're doing ray casting versus ray tracing is much more computationally expensive.
Yes.
Because you have order p pixels and then n objects in the scene, and each bounce is a potential intersection test with n objects, and so it gets out of hand pretty quick.
Yeah, and so it's the global knowledge that's really expensive. That the nice part about rendering is that you only need a little bit of knowledge to render something. Whereas the primitive in ray tracing, you need potentially to touch everything, and certainly you're going to be touching a lot of things. And it's not known ahead of time what those things are going to be. You compute it, and then you go fetch it, and you compute it, and you go fetch it. And that's a very long latency type operation.
So what can ray tracing do that the geometry method cannot do?
Okay. So for instance, so what I said is, hey, it's great because two objects don't interact with each other. Okay, and so then I've got this light up here, right? Okay, this screen doesn't know about my hand. Okay, how does it know to render that shadow on top of my hand? How does it know that this hand is in shadow and this hand is not in shadow? Okay, so it's the sort of cases where two things do need to interact with each other that's very difficult. I mean, that's the hard part. And so what you see in, okay, so here's another example. I have a little mirrored globe in my hand. Okay, a globe. Okay, so this globe, what it would actually look like if it was a silver globe is that it would reflect all of your faces in this globe. Okay, well, then it has to know about all your faces. And what I just said is, well, it doesn't know about all your faces. And so to do these sort of effects, to do shadows, to do sort of reflections, light transport, cool kinds of things, refraction, all that. Those are things where you have to put hacks into the graphics pipeline to make it work, and they don't work in the in the only a geometry pipeline kind of world. So that's hard, and that's why people are interested in ray tracing, because it's going to give you more realistic stuff that you can't do very well using geometry. Okay, so why is it suited for real time? It's parallel. Primitives don't affect each other, and rendering a primitive doesn't require global knowledge. Okay? So we're going to have lots of geometry, but all the geometry can be done in parallel, separately, without interfering with each other. And so when we build hardware, we're really going to want to take advantage of that. Okay. So then, all right, we decide we want to do geometry, or historically we've been told we're doing it this way. Okay? What are our primitives here? Okay? So actually 1D is wrong. Those are now going to be 0D points. Right? So we could say, hey, our primitive is a point. Okay, Okay, we're going to make all of our objects out of points. Come on. Shouldn't have saved it. Okay, so a point is sort of a zero-dimensional object. And this B, for instance, is invented from a particular point primitive called a circle. So Hans-Peter Pfister is now at Harvard, but very nice work there. This is the face of St. Peter. It's one of Michelangelo's statues. So Simon is now at Princeton and is an awesome guy. And so this rendering is done basically with this big sea of points. And the neat thing about it is it's just this enormous data set, much bigger than you can handle in real time. And it starts off rendering in this very coarse way, and then if you give it more time to render, it gradually refines the points down where you can get a reasonable facsimile of what the surface actually looks like. So it's a project called QSplat. And so these are projects where they said, okay, the fundamental rendering primitive should be a point. And then what we have to figure out is how do we render points and how do we sort of fill in surfaces from points so that we get a nice full surface. Okay, so this is one way we can actually do rendering. We could also say, hey, instead of rendering points, we're going to render surfaces. Okay, we're going to render something that's in 2D. And we're going to make our surfaces out of some sort of 2D primitive. So a triangle. Okay, we can make our whole surface out of triangles, or my whole head is mapped using little tiny triangles. We can use quads, which is a 4-sided surface. Okay, we could use what are called higher order surfaces. Okay, so what we have over here is a picture of subdivision surfaces. So this is sort of what you specify as the programmer. Okay, and then the yellow lines are ones that you want to leave as creases, where they're hard creases. But the ones that are the lines that are not are ones where it's going to take sort of this skeleton and then subdivide using a particular set of rules and end up getting a nice smooth surface. So you have this nice smooth bump here, but you've asked for a crease to go on here. So subdivision surfaces are really nice because it takes very little information to specify them, but you can still come out with very nice smooth surfaces. So Pixar had a short movie a few years ago called Jerry's Game. And it had two guys who were the same guys playing chess against each other. Okay, so some of you might have seen that. So that was sort of the first movie where people used subdivision surfaces as the fundamental primitive, and that was within RenderMan. People really like modeling using subdivision surfaces. If what you want to do is create an object, subdivision surfaces are a really nice way to do it because you can take these points and sort of stretch them out, and you're going to get nice smooth answers here. And you don't have to model every individual little triangle, and you're guaranteed that they're going to be smooth. They're mathematically a very nice thing to have. Okay, so having higher order surfaces is really kind of cool. Okay, I'll give you a little hint here that where we're going is eventually we're going to pick triangles, and we pick triangles because they're very simple. They're very simple to send through a graphics pipeline. Okay, but there are lots of arguments where other things might be good. And if we did images, those are sort of 2D geometry also, if we chose those as a particular rendering basis. Okay, or we could do volumes. So Jim Kajia, a very famous graphics researcher, he said at the time that all rendering was going to be volume rendering, okay? Because volumes are sort of supersets of all the other things. And this is a beautiful volume rendering of a particular dead guy, I guess. Oh, this is kind of gross, so it's a good story. So my understanding is they have this visible human data set, and they got this data set. They wanted to take a cadaver and then cut it up. And the problem was that the cadavers they had all died for some reason that was, natural death, but was, the body was, your heart had a heart attack or you had cancer or something. So your body wasn't quite right, like something had gone wrong. So what they actually ended up using for the visible human was a convict that was executed. And so his body was all in good shape, and then they took him and cut him into little slices, and they got a great data set out of it. So that's giving your body to science. So you can do volume rendering where, and that will sort of it's a superset of all sorts of kinds of rendering here. And so there was thought that this would end up being really the way things have gone. People have built volume rendering hardware as well. But hasn't really taken off. And this is something that's used often in data visualization contexts, but not so much in mainstream. Okay, and then I want you to think about the rendering spectrum generally as a, come on, won't go forward. Not just as a couple of discrete points, but rather it's something continuous. And so this is a very interesting paper. Jed is at Microsoft Research, and so what he wrote was about graphics and vision and how they're sort of converging. And so he had a spectrum of going from things that are image-based, appearance-based, and rendering based on that, and things that moved all the way over to being physically based on geometry. Okay, so this is things based on appearance, things based on geometry, and all these techniques that are in graphics, and he sort of put them on this big spectrum. Okay, so we can build rendering systems that are anywhere on this spectrum or that use different techniques in this spectrum. And certainly many of these techniques are things we can build into the graphics pipeline if we choose to. So the paper's really good. Okay, so that's rendering primitives. Here's one of the other decisions we have to make. And so this is a decision about what we call immediate mode versus retained mode. So immediate mode is sort of the idea that we say, okay, draw this triangle, and it'll go into the system, and it will be drawn to first order right away. And as we specify more triangles, okay, and we specify more geometry, it gradually appears up on the screen. Okay, so it's sort of like an interpreted thing. Like every piece gets interpreted sort of roughly when it's specified and so on. Or we can think about doing a mode called retain mode where we say, okay, you have to give me the entire scene, and then once that's done, I'm going to do some processing on it, and then you're going to get the whole image back. Okay? So this is like what a ray tracer is. You can't like partially specify a scene for a ray tracer and expect it to render correctly because there's all the light transport issues. You kind of need to know about the entire scene to render the scene correctly. Whereas traditional GPUs have immediate mode. And OpenGL at its core is an immediate mode interface. Okay? It has some retain mode characteristics, and it is becoming more retain mode as time goes on. Not for API reasons, but rather for performance reasons, because it's very useful to be able to look at a big chunk of the scene or the whole scene at once, make some decisions based on that. But OpenGL at its core is immediate mode. If you send one triangle, it's going to show up, right away, right before it doesn't have to wait for the whole scene to make progress. Okay, so here's another question that's going on, and I looked last night for a long time to find better pictures than this, but this is all you got. So we specify a whole bunch of things to draw, and we specify them in some sort of order. And the question is, does the rendering system have to respect that order? Does it have to render everything in the same order that I specified? Okay, and you might say, it doesn't matter. Does it matter if I do this hand before this hand, or does it matter the other way around? Okay, it turns out for some things it matters a lot, and it turns out where it really matters is for transparency. So if you have objects that are partially transparent, then which we'll cover later in the class, the transparency equations are set up such that you want to render them from back to front. Okay, you need to sort things and then render them from back to front, and then things are going to look correct. Okay, if you don't do that, then you get visual artifacts. And so if we look at these two pictures, this one is evidently done correctly, and this one is not done correctly. And the question is, what's going on here? So what's bad about this scene? What looks incorrect compared to the correct scene on the left?
Can't see the far end.
Okay, you can't see the back of this.
Yeah.
Okay, here we can definitely tell that there's sort of a front and a back. Okay. Other things? Okay, the blending is out of order. So what's the artifact that we see as a result?
Like on the lip of the T5 here, you see those chunky polygons there.
Okay, so that's some sort of artifact as a result of this. Right, so if we look, we can tell that this is sort of farthest away because it's the closest to the background color, and there are several layers we're looking through, whereas here it's hard to tell that because all three of these seem to be the same sort of dark. Not an expert at this. I wish I could have found better pictures. The point being that people really want, so if you're going to do the transparency equations correctly, then you as the programmer will make sure you specify them from back to front. And what you don't want is your rendering system to then go around and saying, yeah, I'm not going to respect your ordering. I'm actually going to render them some other way, and then your thing looks wrong. Okay. So it is desirable to have something ordered, to say that I promise as the rendering system, I will render things in the same order that you do them. But it is hard to make that work and make it be efficient. And the reason is because you have all this parallelism going on, and if it turns out it's easier to render this thing first or this thing first, you want to be able to make that decision. You don't want to serialize everything. You've just come up with this great parallel interface. Why do we have to serialize it so that everything is in order? So this is a real challenge for the hardware, because it wants to blow things up parallel, but it needs to make sure that it's still going to respect this ordering constraint. So there are rendering systems out there that do not have the ordering constraint. They say, you know what, that's too hard for us to deal with. We can be more efficient if we take out the ordering constraint. But there's things you can't do very well if that happens. One of them is blending. Okay? So OpenGL is an ordered interface. It promises that if you specify A, B, C, it will appear to render in the order A, B, and C. And if it does take them out of order, it can't affect the result. Okay, so if I render my two hands up here, it doesn't really matter what order they're in, right? These two things aren't going to affect each other. So maybe OpenGL can detect that and say, oh, I'll do that one first, or I'll do that one first. But at least has to appear like it was all rendered in order. Okay, so we talked about this a little bit last time. What's a frame buffer? So a frame buffer is this data structure that we have that sort of holds information for every pixel. And what do we want to really hold in this frame buffer? Well, we'd like to hold like the color of every pixel. And to be able to render into this frame buffer where we start filling in pixels with the contents of our geometry. Okay, cool. So usually we want to store the color and we want to store the depth. And by depth I mean how far away the pixel is from the camera. Because if I have a pixel from this desk right here and then I render my hand, I want to be able to say, oh, the hand is actually in front of the desk. We should replace the desk with the hand. Okay, that's what the depth information is going to tell us. We might even want more than one frame buffer. Okay, what we might want to do is be displaying out of one frame buffer and being drawing into the other frame buffer. Okay, and then we swap them. We always display out of one and draw out of the other one, and draw into the other one. Okay, so that's a possibility. But it turns out that you can have other ways to do this that don't involve a frame buffer. So we talked about beam chasing last time, that what we can do is, as the raster is moving across the screen, we can just calculate right in front of the raster what the value of the color is. Okay? And that's what these beam chasing machines do. And then we don't need a frame buffer because we never have to store the whole image at once. We only need enough space to store that gap right there. Okay? Or we can always sort things. Okay? If we always sort things, then we don't necessarily, I mean, there are algorithms that don't require this. So early algorithms, the frame buffer was very, very expensive. And so sort of the inventor of computer graphics, his name is Ivan Sutherland. He did his PhD at MIT, and he did a system called Sketchpad. That was his dissertation sort of founded computer graphics. It's awesome. And so he actually got out of graphics after writing this particular paper in 1974. And what he did was look at ways to solve what he called the hidden surface problem. Okay, so that's the problem where I'm drawing my hand and I'm drawing the desk. Which one do I really want to draw? Okay, so what he showed all these different ways to solve the hidden surface problem, and what he said is they all come down to sorting. They all come down to, for example, sorting front to back or sorting back to front. If we always have the front things in front, then we can throw away the back things and not have to render them and so on. And he showed that all the different hidden surface algorithms that people had come up with all ended up coming down to sorting. Okay, and this little quote up here was, he's saying that this approach, okay, what he calls the brute force approach, was ridiculously expensive. And what he referred to of the brute force approach was having storage at every pixel. It's having a frame buffer. Having a frame buffer was, in 1974, what he called a brute force approach, because nobody could even imagine having enough memory in your machine so that you could store a color at every single pixel. They went to all these sorting algorithms just so that they could avoid having to do this, having to have that much storage, because that much storage was very, very expensive. Okay, so he goes to all this effort to figure it out, and today we just say, ha, can't believe you're doing that. So much easier to do it the way we're doing it now. Okay, so that's you know, all this happened before most of you were born, but that's how things used to be in the bad old days. Okay, here's another decision we have to make. Okay, and this is a decision about what we call graphics state. So what is state in the context of a computer, like computer architecture? What do we mean when we say state? Okay, the state of a program.
You have some kind of state machine, and then it'll have, you know, certain input or something, and depending on the input or whatever state it is, it'll move on to another state. And
okay, but what is the state? What do I mean when I say state?
Like, you know, state, I don't know. It's like a point in the system. I mean,
okay.
What it's doing.
Got a program counter and registers and that sort of stuff.
So what is all? I mean, all that is state. What does that actually mean? What do I mean when I say state?
That tells you I can't define it without using the word state.
Okay. Somebody else want to try?
A snapshot of the whole system at a particular time.
Yes, but I think that might encompass more than state, right? That might encompass some of the inputs and outputs. Like, what's special about state? Okay, we've got a whole bunch of inputs to process. We have state. We have... So, okay, for me, state is, let's say we turn the computer off, and we want to turn it back on, and we want to put it back to where it was where we were. Okay? It's the information you need to recreate the position of a system at any given time. Okay, so for example, if we want to turn off the computer and then start the program off where we left off, we're going to need to know the program counter of that system. We're going to need to know where it was. We're going to need to know the contents of the registers and the contents of the memory. So it's usually some sort of storage that is associated, that's not associated with any certain input or any certain output. It's storage within the system itself. Okay, so the question is, how do we, should there be state in a graphic system? And you can build a graphic system with or without state. So let's say I was building a graphic system with no state at all, okay? And I want to render, I want to render this particular screen right here. Okay, then I'll send a bunch of primitives here. I'll say, okay, I want to send this red triangle here, or okay. Let's see. I want to send the letter A, okay, and I'm going to use this particular font, and my font is going to be black, and my point size is going to be 12, and here's the picture of the letter A. And now I would like to render this T. So my font is this, and my point size is this, and I'm going to color it black, and here's the T. And now I'm going to render this T, and well, here's my font, and here's my font size, and it's black, and so on. And so wouldn't it be a little bit easier if we said, set color to black. And then after that, okay, start rendering this, and just use the current color. Okay, so then black would be a state. Okay, it would be part of the system that would not be associated with any particular input or output. Instead, it's sticky. I'll set a piece of state, and then that state will apply to everything that comes after it. So what might be interesting to use for state? Color, whatever the current color that we're drawing is. Okay. What do I have up here? Fonts. I'd like to be able to specify my fonts once and have it set on the graphic system, and then just be able to refer to that instead of having to send the fonts every single time. Okay, if I'm using a texture to draw something, if I'm using a texture on my sweater here, I want to specify the texture once, and then all future drawing calls that I'm using that use my sweater can just use that texture that I specified. So using state minimizes data transmission because you only have to send it once, and it sets it, and it stays there forever. Okay, so that's a good thing. But the problem is when you have state, you have to deal with that in the graphic system. So you have to store the state. If you context switch, you have to save the state out, and so on. So what do we actually use state for? Well, besides these resources, we could, once we set a light, it stays there. Once we set a material for some material we're drawing, it stays there. Once we set a color, it stays there, and so on. When we specify a modeling transformation, we say we're drawing the camera in this place. That's state in the system. It'll stay there until we change it to something else. Okay? OpenGL has state. Okay? And how does OpenGL do it? Ideally, you don't want very much state, and you want to make it bounded. The really bad thing, if you're implementing something in hardware, is to make it infinite. Potentially, we can have 10 gigabytes of state. That's not good. So OpenGL is very specific about the state that it has. It's 12 kilobytes. Okay? That's how much state you have to store in the. And so to make it actually work like that, to make sure it's bounded, they say, okay, you can have up to 8 lights. That's in the spec. If you have more lights than that, well, maybe we'll support it, maybe we won't. We'll guarantee we'll get to 8, but nothing's guaranteed past 8. Okay, maybe your system will do more. We're not going past 8. And they can guarantee that the amount of state they have is actually bounded. Okay, so there's things that are hard about this. Like you really have to think, if you're going to have state, then you have to think about some of these things. What happens when you change state? Okay, well, when you change state, it has to apply to everything that comes after you and nothing that came before you. It's hard to deal with in a parallel system. Okay, you have to make sure that you do that properly. Because you're going to have a big pipeline of things happening at once, you're going to have different states that are active at the same time. Okay, so these primitives all have green as their color. These primitives all have red in their color. How do you keep track of that? Okay, so these are difficult things. Okay? But there's enormous advantages for having state, and so this is a system that has state. Okay, here's my last one in terms of design decisions, and this is what we call invariance. So the question is, if I have OpenGL on my cell phone, and I have OpenGL on my supercomputer, and I have OpenGL on my laptop, how similar do they have to be? Okay, do they have to be pixel for pixel identical? Okay, do they have to be identical at all? What sort of things do we specify must be invariant across all OpenGL implementations? Okay, so that's something very important for the designers to say. So it's reasonable to say that you're pixel for pixel identical. Okay, but then you run into the problem that maybe somebody comes up with this great new algorithm and they'd like to be able to implement it on the high-end machines, but it's going to make it not pixel for pixel identical. It looks better now. Okay, how do we deal with that? So OpenGL is very careful about saying what their drawing commands do and what their drawing commands don't. So for instance, they don't say which pixels are inside a triangle. The implementation gets to figure that out. There's some rules as far as, this has to be drawn, this has to be drawn. Seams have to work out nicely, but they don't tell you which pixels you have to draw. Okay, they don't specify precision. You get to pick that as the designer, for instance. They do specify invariance across modes. So for instance, if I draw this blackboard by drawing it all in quads, or if I draw it by drawing it all in triangles, as long as I specify the same geometry, I need to have the same pixel coverage. Okay, one can't have holes that the other one does. So that's something OpenGL does require. If you draw things in two different modes, you have to have the same visual output. Okay, so that's a lot of decisions that had to be made. Anybody have any questions about these? Okay, so we'll talk about sort of some of the things that OpenGL decided to do. So this is the paper. Mark Siegel. Let's see, Mark was at SGI for many years. Then he went to ATI. He was one of the chief guys at ATI. And now he's at Google, and he's doing cool stuff at Google. Kurt was one of SGI's founders. He was a graduate student for Jim Clark. Was at SGI until like the late 1990s. He left Stanford to get to start the company before he finished his PhD. So he actually came back to graduate school. So we were graduate students together after he had already established himself as like the best graphics architect on the planet. Let's see. So then he went, after he graduated, he went to Microsoft Research, where he is now, and he got to help start the Microsoft Research Lab in Asia, which was pretty cool. So they're both really great guys. And so they talk about they talk a lot about why they designed OpenGL in the way that they did. So this is sort of how they define what they saw graphics standards need to be able to do. And so here's some of the things that they felt were important. Okay, these are the things that they took into account when they designed it. So it has to be high performance. That was sort of their number one thing. It has to be orthogonal. What I mean by orthogonal is you've got this whole feature set, okay, and you've got this whole other feature set. Okay, so for instance, you can render with floats or doubles or ents or chars, and you can render triangles or quads or strips of triangles or fans or different things. If it's orthogonal, it means that any of these combinations work with any of these combinations. Okay, it isn't like this one works and this one doesn't, and this one works and this one doesn't. You can take feature sets, and any feature set is going to work across all sets of modes. So they wanted to make sure that would work. Complete could do all the things in the graphics system. Interoperable, so you could work with lots of different kinds of computers. Extensible was a big one. They knew that the technology was getting better. And so they wanted to make sure you could take the standard and make it better as time went on, to say, oh, we'd like to add new things to it. And it needed to be accepted, and that was certainly true. I mean, OpenGL was certainly into the late 90s sort of the only game in town, and it's still pretty much the only thing outside of computer gaming. So if you buy a Mac, that's what you use. If OpenGL ES is what it's on a lot of cell phones these days. They've really tried to continue to make this accepted. In terms of the declarative versus imperative, okay, they came down solely on the side of imperative here. So they talked about how things are done rather than what needs to be done. So this is very much an imperative interface. So out of the decisions that we talked about, these were things that they decided right off. They said, okay, this is what OpenGL does. Okay, it is going to be an immediate mode render. It is going to guarantee ordering. It has stateful interface. Triangle is going to be the fundamental primitive, and it has a frame buffer. And these are decisions that go all the way through all the description of how OpenGL actually works. Okay, So now what I'm going to do is sort of walk through the pipeline, sort of what happens in the pipeline, and then I'm going to go through it in more detail. So I'm going to sort of go through it twice, but to motivate what OpenGL does. So first we're going to sort of ignore any shading or lighting, sort of talk about what happens in OpenGL. And we're going to start with a list of triangles, because that's our fundamental primitive. It's going to be some sort of list of geometry. What I'm going to actually specify is a bunch of vertices and how the vertices are attached to make triangles. We're going to have a command processor, and that's going to put them in sequence. And we're going to specify all this geometry in object space. So if I'm rendering a whole bunch of objects, each one of you is a different object, and each one of you is going to be modeled in your own coordinate system. Okay? So your coordinate system is nothing like your coordinate system is nothing like your coordinate system. They're all separate. It isn't like this one global coordinate system. Okay? And then we will end up transforming these operations into one common coordinate system that we can all render with. But that's something that's done under the hood in the graphics system. Okay? All you do as the programmer is you specify the geometry in its own system and then specify how you're going to transform that into some sort of global system. Okay? So we're going to do some operations on every vertex. We're going to do some operations on every triangle. And then we're going to project those onto the screen. Okay? So we're going to take these 3D triangles, project them onto the screen, and now we've got triangles in screen space. Okay? Next step is this rasterization here. And so we start off with geometry that's in image space now. Okay? It's in a coordinate system that's associated with the screen. Okay? And that's a very important transition that we make. So back here, when we specified triangles in general, these are in object space. Okay? Out there in the world, we're object parallel, okay, different objects. Now we move here. Now we're image parallel, and now we're in some sort of image space. And what any rendering system is going to have to do is to go from some sort of 3D space into a 2D space, some sort of 3D parallel space, the 3D parallel structure, object parallel, into an image parallel.
On the previous slide, and we're talking about OpenGL. Mm-hmm. On the previous slide, please. Mm-hmm. So clipping. Right, I'm sorry, I was getting confused. I was mixing fragment operations.
Okay.
Yep, sorry.
I'm not even defining these right now.
Yep, understood.
We will get to what clipping and culling are.
Yep.
Okay, so we're now in image space. We figure out which pixels we cover with each triangle, and we figure out what color they're going to be. Eventually, we're going to figure out what color they're going to be. What we're going to generate here is a new word. It's a fragment. All right, so we're going to have many triangles up here. Triangles are going to cover pixel locations. Every place where it covers a pixel, we're going to generate what we call a fragment. And a fragment's like a pixel that hasn't graduated yet. Okay? There might be many fragments at one pixel location. Okay? If I have several triangles that overlap each other, only one of those fragments is going to win and end up graduating and becoming a pixel. Okay? So you might have many fragments, but only one pixel is going to come out. So fragment is a technical term, but it is an important technical term. Okay, now what we're not dealing with yet is this problem of occlusion. How do we deal with this problem? What do we render? And that's what's sort of done in this composition stage. We start with a list of fragments at every pixel stage. Okay, and we process each fragment individually, and we have to end up assembling all those fragments into a final image. We've got to get one pixel value out of all the fragments at a certain pixel location. So the way we typically do this in OpenGL is that we store how far each fragment is away from the camera, and we take the fragment that's closest to the camera. Okay? That doesn't deal with stuff like transparency. It only deals with opaque surfaces. If you actually do have transparency, then you have to do some blending and so on. We'll talk about that later in the class. But using this depth test, this frame buffer, what's called a depth buffer, a buffer with a depth at every pixel, is how we end up resolving that. Okay, now we haven't dealt with anything about lighting. Wouldn't be very interesting to have, this picture, except for all the noise around it. We want pictures where we actually consider lighting, and we're doing things with that. And so we want to think about shading and texture. How do we shade this thing? And so in OpenGL, typically, we're going to, at least with old school OpenGL, you specify color information at every vertex. Okay? And then you calculate lighting computation at every vertex. So why do we do it at every vertex? Okay? As compared to being able to do it at every fragment or every pixel. Okay, so the answer to this is that it's expected that things like lighting and color don't vary very much across a triangle. So if what we do is we calculate them at every vertex, and then we say, okay, blend nicely between those, it's going to look okay. And then we only have to calculate it at the vertices. We don't have to do a separate calculation at every fragment. Okay. But, and it's because this information is generally fairly low frequency information. It doesn't vary very much. Texture, on the other hand, is when we take a triangle and we say, here's a checkerboard. Okay, and we want to take it and map it onto this triangle, and all these are filled in. Okay, and then we want to nicely map it here and get this nice checkerboard that goes on here. Right? So this is a texture, and then texture mapping is how to take this texture and map it onto some sort of geometry. All right, now this tends to be very high frequency information. It actually needs to be calculated at every pixel, to be able to make this look good. So we'd rather compute it up here because there's less work to do, but in practice we need to do it at every fragment. So this is sort of what OpenGL sets up. OpenGL says we're doing color stuff, we're doing lighting stuff per vertex. Per fragment we do texture stuff, and we texture in image space. So we texture after this has gone through the object to image space transformation. So that sort of leaves us this pipeline. Okay, and I'm going to go through this in a little more detail now. All right, so we start off with the application. Command processor sequences things. Geometry work is things we do per vertex. We then rasterize into fragments. We texture each fragment. We do fragment operations like the depth test and so on. And then at the end, we're going to display. Okay, so OpenGL has other branches to it. OpenGL also has like an imaging branch, so you can do image processing kinds of stuff in OpenGL also. And so this is sort of our geometry branch that we've just talked about. Use of sort of different terminology, but the same thing. But OpenGL also supports lots of imaging things. And if you actually look, unfortunately, at the whole OpenGL pipeline, it's very complicated. But if you went and looked, each one of these is a very simple piece. And this only gets more and more complicated each year as they add more and more things to it. But here's where you can see, like, okay, this piece of state is used here, and this piece of state is used in this piece, and so on. Like, it's very specific about what's going on in each one of these pieces. Okay, so now I'm going to talk about actually what happens in each stage. And I've got pictures now, so these are kind of cool animations. So first, what happens in the application stage of the pipeline? Okay, so application is what runs on the CPU. Okay, so this is usually some sort of simulation that's going on. I always say that often the simulation is people running around shooting each other, but perfectly legitimate simulation. So what happens in the application? Okay, input events like you're moving your mouse around or keyboards, handled in the application. Usually what you're ending up doing is you populate a bunch of data structures in your application. You say, okay, well, these objects are here, and so on. That's all done on the CPU. You're going to have these data structures that make up a database. You're going to traverse the database to figure out what you're actually going to render. Okay, so I only want to render things in this room. I'm just going to query the database for the things in this room because I don't want to render the things over in some other building there. That's a waste of time because all those are going to be occluded. We're going to generate primitives here, and if we have any utility functions, which is a GL-specific thing, we're going to do it here. So these are all things that do on the CPU before it sends commands to the graphics system. Okay, so what happens in the command system? Okay, so what it's going to do is take the list of commands and sequence them and send them to the rest of the graphics system. It will interpret them. If it needs to convert formats, okay, so I specify something in ints, but it needs floats, it's going to do that here. It's the part that maintains the graphics state. And in this picture, this is the graphics state. Okay, we're going to keep graphics state of the current color, and we're going to keep the current transformation matrix. So what we're going to do is sort of walk through a little example here. Okay, so GL load identity is a GL command that will set the transformation matrix to the identity matrix. Okay, so no transformation at all. Then we're going to multiply that matrix by another matrix T, and identity times T is T. Okay, and then we're going to start and we're going to say GL, and these are the sort of things that I will go over with in the next hour. If you don't know what any of this means, come next hour. So then we're going to say, okay, we're going to start rendering, and we're going to render what we call a triangle strip. Okay, so a triangle strip is where I specify a bunch of points here, and the rendering system will make triangles out of those. So every additional point I make is going to make another triangle. Okay, so we're going to start that, and we're going to say, okay, let's set the current color to green. Okay, and then we're going to call a vertex. We're going to put down a vertex here. Okay, and it's going to be at the position 0, 0, 0. And then we're going to set the color to red. Okay, and note that changes the state. We're going to specify another vertex, and note that vertex uses the current color. I don't have to say GL vertex 3F 1, 0, 0 red. Okay, that's the advantage of having a stateful interface. Instead, it just uses the current state. Okay, change the color again to green, specify another vertex. Okay, now I got 3 vertices, that makes a triangle. Specify a color again, specify a 4th vertex, makes another triangle. Every additional point I make is going to make a new triangle and so on. Okay? Any questions about what goes on here? Okay, so this is all done in the command stream. So it's keeping track of this, and it's going to sequence these all the way down the rest. Okay. Next stage is geometry. Okay, so eventually we get to call GL end, and that ends the triangle strip. Okay, so in the geometry stage, here's some things that happen. One is that if I specify any curved surfaces, they're actually evaluated here. We're also going to take these objects that we specified in object space, and we're going to transform and project them onto the screen. And we're going to do clipping, culling, and primitive assembly. So clipping is where we have a screen here, and we draw a triangle like this. Okay, well, that's kind of bad because half the triangle's off the screen and half the triangle's on the screen. So what we need to do is chop the triangle into these 2 triangles, this one here and then this one here. Okay, so that's what clipping does. Culling is done to throw any triangles that face away from the camera. Don't really worry about that now. We'll talk about that later. Primitive assembly is taking that list of vertices that we had that was a triangle strip and turning it into a bunch of triangles. Okay? So these are all things that are done in the geometry stage. So for instance, what we do in here is we specify these lines or triangles here, and we specify the camera location and where the screen is. And what that's going to do is sort of project these geometry onto the screen. That all happens in the geometry stage. Okay? The other thing that goes on here is we have to do all the lighting. Okay? We also do some texture stuff. Don't worry about that. But we have to do the lighting. We have to compute the interaction of this color with this light, and we're going to get some sort of color out of it. Okay, so we do all those calculations on a per vertex basis in the geometry step here. Okay, next step is called rasterization. So we're going to do some work per triangle, and we're going to do some work for every fragment that we generate. So I think this one's animated, actually. So what we're going to do is we're going to figure out, okay, we're going to make sure that it's projected in the previous step. And so which fragments is it going to color? And what color are each of those fragments going to be? Those are the decisions that we're making. So those are 2 separate parts of rasterization. Which pixels am I covering? Okay, so I'll generate 1 fragment for each of those. And what color are each of those fragments going to be? So it's got to somehow walk through this triangle and figure those out. Here it's drawing 2 triangles, and so it's doing them each separately there. Okay? So this process of saying, okay, that's green, that's red, so this is sort of green and sort of red is called interpolation. Okay? So each one of these, the color is called an interpolant, and we can figure out intermediate values here as a function of those interpolants and where the position is. Okay? So that's something the hardware is very good at, and we're going to talk about how we do that in this class. Okay. Next part is texturing. So we're saying, okay, now we have these cool interpolated color fragments here. We want to apply this checkerboard texture to them. Okay, so now what we have to figure out is, okay, what are the coordinates of this texture? When specified here, we could say, okay, that corner corresponds to this vertex. That corner corresponds to this vertex. That corner corresponds to this vertex. Then we have to figure out how this thing maps onto this thing, because you can figure decaling it in many different ways. You get to specify that. You get to specify where the corners are, and it'll figure out everything that happens in between. And so there's lots of calculations associated with texture. This is a big piece of the pipeline. Here we're having a nice simple orthogonal mapping there, and then we're going to have to figure out how to blend these things together. So we're going to blend the texture with the colors. Now, old school OpenGL You sort of had the ability to do some color things here and have some texture things there, and there were some fixed ways that you could interact the color with the texture. What I want you to think about where things are going is this has become more generalized here, where it's less of, okay, here's these textures, here's these colors, here's the fixed number of ways you can do it, as opposed to you get to run an arbitrary program at every fragment. Okay? You get to write a program where you can use texture in any way you want, you can use the colors that you came up with in any way, you can read things out of global memory, and you get to bring those in and do really complicated programs. And those programs are getting more and more complicated as time goes on.
It just seems odd that we're doing the checkerboard after we do the rasterization, because when you're applying the actual colors, like the green and the red, it seems like that would be the natural point to do the checkerboard and then rasterize the image.
Okay.
Is there a reason why that?
So we want to go back to, if I go back, it's going to have to redo all those, so I'm not going to do that. So you're suggesting when I compute the colors at each vertex, maybe it would make sense to texture there. Okay, so then the issue is, well, if we look at this here, like we have a triangle here, right? So we could have a texture value that we did at each vertex. That's what you're suggesting. So we have one texture value here, one texture value here, and one texture value here. Okay? That doesn't give you enough information to do a high-frequency, complicated function in here. Like if you look at this, these are darker than this. You only have 3 points if you do texturing at the vertex stage. And so what you really want is to compute something at every fragment, because only that's going to give you the high-frequency information. That's a decision that the OpenGL folks made. They could have said, all right, we're going to texture at every vertex. We'll go with that. That would have motivated having very small triangles because you want to be able to get high-frequency information. But there are other interfaces that do texture at vertices. OpenGL is just not one of those.
So as we add vertices, can we give different colors as we go?
Yeah,
like
so every vertex you specify will use all the state with the system that might be associated with a vertex. So there's a color that's associated with vertices. There's a normal vector, which is sort of what direction the vertex is pointing, and that's very useful when you do lighting character calculations. There's a texture coordinate associated with every vertex. So you can say, okay, this is 0, 0, this is 1, 1. So, there are many things you can associate with a vertex. And so, yes, everyone gets its own information. Okay. So then we're going to have to do some fragment operations. One of those is the frame buffer. Okay, but we also do, there's hardware fog built into OpenGL. Okay, but you didn't know that. There's a bunch of tests that you can do against OpenGL, against every fragment. So do I own the fragment? Okay. For example, if here's my window, I probably don't own this fragment over here. Some other application does. So it checks who owns the fragment. Is it my application or somebody else? Okay, sounds like a good thing to do. You can set up other tests that are based on other things in the graphics pipeline, like throw away this fragment if its transparency is less than this or something. The important one here from our point of view is depth. Okay, so we can say, well, there's already something in the depth buffer here. Okay, all right, cool. And so then we will try to render these fragments into the depth buffer. Okay, so it will decide, oh, that white primitive is actually in front of the new primitives that we just rendered, so it's not going to go into the frame buffer where the white thing was, but it will go into the frame buffer at the places where it had a gray background, for instance. Okay, and there's a few other things that go on here. If you have partially transparent things, then it will blend them into the frame buffer. So if you have a piece of red cellophane over a piece of green cellophane, then it will blend those together and get some sort of shade of ugly brown or something. Okay, and then you've got a frame buffer, and you have to figure out how to now change this digital frame buffer into, historically, some sort of analog television signal. Although today, everybody has these cool flat screens, so you never really have to go to very much analog at all. There is a procedure here that's called gamma correction. We will talk about that later in class, but it's basically tweaking the values of the colors so it ends up matching some really nifty things in our brains that how do we interpret colors. So it's kind of a cool discussion when we actually get there. But eventually I have to turn these values into light. Okay, and that's sort of the final stage. Okay, so if we look at the pipeline here as a broad thing, in general, these are things that act in object coordinates and act with object parallelism. Okay? These are things in general that are acting in image coordinates and exhibit image parallelism. So when we're thinking about doing graphics processing, okay, we have to have a machine that does a good job of exploiting object parallelism, so it can do a bunch of objects at the same time, and we need a scene that exhibits image parallelism. Okay? So we might think of having, okay, one processor for this corner of the screen, and one for this corner, and one for this corner, and one for this corner. Right? Maybe we can get speed up that way. Okay? We might have every time you send in four objects, each of those objects can be processed by a different processor. Okay? But we also have this ordering constraint. Right? So we have to make sure that it appears like, when we run everything through, that it all appears to execute in order. And that's hard in a parallel context. Okay? We can also sort of divide these into stages. So this in general is some sort of vertex or geometry stage. This in general are fragment kind of operations that are done on fragments. So these are done on vertices. These are done on fragments. And so where we're going is, instead of having these fixed function lighting functions and fixed function texture functions or other fragment operations, we're moving toward a world where you as the programmer get to write an arbitrary program that runs on every vertex, write an arbitrary program that runs on every fragment. And we'll be talking about that in a couple, 3 lectures, sort of what those vertex programs look like and what those fragment programs look like. Okay? So this is really how we're abstracting the program. Where we're going in the long run, actually I'll come back to that. Okay. Where we're going in the long run is the ability not just to sort of write your own programs at each of these stages, okay, but the ability to juggle the pipeline in a way that you see fit. That if you say, you know what, I'd really like to get rid of rasterization entirely or move it after this. I'd like to do fragments up here in object space. Or I'd like to add a new stage here. Or I'd like to turn this whole pipeline upside down. Where you don't just get to mess with one of the stages, you get to mess with the way the stages are interconnected. Okay, so that's not something that graphics hardware supports today, but it's something graphics hardware is expected to support in the long run. And it really changes the way you think about building graphics processors. So that's something certainly our guest speakers will be talking about. It's stuff that the Intel people are really excited about. And it's sort of the next big thing in graphics hardware.
From reading the DirectX pipeline and the OpenGL, I got the impression that they were different. So how is it that if I'm running an OpenGL application and a DirectX application on the same video card, that both can have different pipelines? Yet it sounds like the hardware is set in its pipeline. So, I mean, I'm showing an OpenGL pipeline here, but honestly, the DirectX pipeline doesn't really differ very much. Okay, DirectX, starts with geometry, goes through some vertex stages, goes through rasterization, does some fragment stages. The API might look different, but what's actually happening under the hood is not very different. Okay, there's some things one of them does that the other one doesn't, and vice versa. Practically, what happens is, one thing I said about OpenGL is that it's extensible. And so what happens is if DirectX puts in a cool feature, the vendors will launch an extension that works in OpenGL. So DirectX says we want to do this widget function here. Well, like 2 days later will appear the GL_widget_NVIDIA extension that is used to take OpenGL and put the widget function on NVIDIA hardware. So OpenGL stuff, at least with the extension, stays on par with DirectX functionality. Okay. Cool. So then we want to get a little bit more to my research interests here. So what people have been interested in is they're saying, well, we have this enormous amount of compute here. Okay, there's a lot of compute in geometry program. There's a lot of compute in this fragment program. And we get really good parallelism out of these things. They're programmable. We have high performance. So we'd like to do other stuff with them. Okay? We'd like to do things that are not graphics with them. And so one of the hard parts historically has been the only way that you can get to these guys, okay, is to write like an OpenGL program or DirectX program. And you'd have to write it in these very strange ways so that it looked like a graphics program, but it was really computing something that wasn't graphics at all. Okay, so that was difficult. You'd do fluid simulations, but what you'd really be writing is an OpenGL program and using colors to describe things that weren't colors. So there are new programming environments that have come out over the last year or two that make this a lot easier. So what they do specifically is they don't really run through the graphics pipeline so much anymore. They just target one piece of the pipeline.
Okay, they target the hardware inside the pipeline, actually the programmable units, and all you're doing is talking to those things directly and avoiding all the fixed function stuff that's around it. Okay, so we'll certainly be talking about that more. Okay, so these are not the only ways that we could have made these decisions. Okay, OpenGL made a certain set of decisions. There's other things we could have done. Okay, so for example, how do we do hidden surfaces? All right, so we could use what's called the painter's algorithm. It's the painter's algorithm because if I'm painting a picture, I start at the back of the scene, and I work my way forward, and the last thing I paint is the thing that's closest to me. Okay, so if I render that way, okay, if I render from back to front, okay, then I don't have to ever have a depth buffer because I always write a new, every time I get a new fragment, I write it because it's always something closer than the fragment that came before. Okay, so I could have built a system in that way. I could have said, hey, the application is responsible for sorting from back to front, and if that's the case, I don't even have to have this depth buffer. Okay, but the OpenGL guys said, no, we're going to have a depth buffer that's part of this. We're not going to require that of the programmer. Or we could go the other way around. We could, that was not the distinction I wanted to make. The distinction I wanted to make is that if we have the painter's algorithm, then we are doing all the hiding stuff way at the application stage, early in the pipeline. Okay, we're making those decisions early on when we do the sorting of geometry before we even send it to the graphics pipeline. We've already sorted it when it enters the graphics pipeline. So that's sort of a hide first structure. Okay, instead we choose to do it hide last. We're only determining the hiding once we get to the very end. And you can see there's really some inefficiencies with that, because we're going to end up rendering a lot of stuff that never even appears in the scene. Okay? If I'm drawing this whole campus here, okay, and I go draw Wellman Hall way out there in the distance, I'm going to go to all this effort to draw Wellman Hall, and then it's all going to be thrown away because of that wall right there. Okay? So there's some disadvantages to this. We're potentially doing a lot of work that we're throwing away. And so what's happened in more recent hardware implementations is it still has all this stuff, but it tries to decide earlier on in the pipeline, hey, is this thing going to be visible? Can we tell earlier if it's going to be visible? If we know that it's not going to be visible, we'll throw it away and try to avoid some work. Okay, texturing. We just talked about that, right? Do we texture at the fragment level, or do we texture at the vertex level? Okay, I'm contending texturing at the fragment level is a better thing to do visually because you're going to get higher frequency information by doing that. But you could think about having systems that didn't. Okay, so if we have little tiny triangles, then we could probably get away with texturing at the vertex level. And we don't, because the triangles are so small, we already have high frequency information. So it turns out that's what Pixar does. Pixar textures at the vertex level. Okay, because they have little tiny triangles that are the size of a pixel. So they don't have to worry about stretching it over many, many pixels. Okay? Instead, OpenGL decided, okay, we're going to do fragment textures, and we're going to have big triangles, and maybe that's going to be more efficient. Okay? Or shading. Okay? Where do we shade in the pipeline? Right? Do we shade every vertex? Do we shade at every vertex? Do we shade at every fragment? Or do we wait until we get past the depth buffer and say, oh, we know that pixel is going to make it into the final image. We're only going to shade then. Okay, well, that makes some sense because, hey, why should we do all the shading calculations to things we're going to throw away? Okay, we should only shade things that we care about. Okay, the problem is that you have to carry a lot of information with you to be able to do the shading once you get to the end if you choose to do this. So OpenGL has sort of chosen to do those two things. Okay, so not the only decisions they would have made. In retrospect, the decisions they made were really good. This is a fairly long-lived interface. If you look at something like DirectX, it's not super different in terms of the direction that it made. And it's lent itself well to hardware that has been both improving in performance and improving in features over the years. So you'd have to say that they did a pretty good job with it. Those guys took it really seriously when they did it. And it's really nice talking to them about the decisions that they made. Okay, so I'm done for today. What we're going to do is what the people that are wanting a little more OpenGL experience, we're going to walk over to 1131. Are you going? Can I get you to go up and get the projector from Destiny in the ECE office? Okay, and when we go over there, I'm going to get somebody to order pizza too. Otherwise, your assignment 1 is due on Tuesday. Submit it through SmartSlide. If there's any problems, let me know. And I will see you guys on Tuesday afternoon. PDF.